Okay, well, let's summarize all the amino acids that we've seen. Here's the table 20 amino acids sorted by abundance in protein. And to stick with the theme, I'm going to just start drawing them. So they all have the alpha carbon, carboxyl group. Just to switch it up, I'll draw the ionized version of it that I think I started off with in the first episode. And here's the amine group. So the simplest amino acid was glycine, just a hydrogen side chain. And then we had alanine, valine, leucine, and isoleucine. Then we had serine, and threonine, and cysteine, and I'm going to draw proline. I think maybe okay, sorry, something like that. So that was proline that we just saw. Methionine. And then there's lysine. I'll draw that positively charged as well. And then arginine. And I'm just drawing them kind of how they are similar to each other, but not how they would be produced in any kind of metabolic process. So again, this will be arginine here. Something like this, maybe. And now I'll draw aspartic acid. So here's negatively charged side chain aspartic acid. And then there's asparagine. Which is aspartic acid, except there's a amine group there next to the carbonyl. And then I guess I'll cheat and I'll make this glutamine. then change that to glutamic acid. Alright, I'll draw histidine. Which might be a little trickier, if I remember correctly. Something like this, maybe. And there's going to be some double bonds in there. Let's try this. Something like that. And if it was positively charged, you'd have a hydrogen ion attached to this nitrogen here. And then tryptophan is kind of similar. There's going to be like a benzene ring kind of merged with that. Let's put the nitrogen down here. And the nitrogen, I believe, has a hydrogen attached to it. And I think there might be a double bond in there. I'll maybe bring that up in a second. So let me just clear that out. Then I think all that's left is phenylalanine and tyrosine. So again, we have this benzene ring or phenyl functional group. So there's phenylalanine, and if we just throw in the hydroxyl group here, we would have tyrosine. So just make sure I didn't make a mistake on histidine. Or maybe it was tryptophan. Yeah, here's a. I forget which one I thought I messed up, but if I didn't just bring it up correctly, you can search for it. So here's the table of all the amino acids. Again, you have the positively charged group here, negatively charged, polar, uncharged, special cases, hydrophobic, aliphatic, and hydrophobic aromatic. And glycine is a special case because it has such a small side chain that it's kind of, I would say, irrelevant side chain. It's more of like a empty space maybe in the protein. So it's neither hydrophobic nor hydrophilic. Proline is going to kind of give a make an irregular backbone where it kind of shifts it from being a nice smooth backbone to having a jagged kind of turn in it. And cysteine, not sure exactly why it's a special case, but it's Seems like it could go in the hydrophobic, and selenocysteine maybe would go in. Well, maybe it becomes charged. Uh, so here's just back at the amino acid page section on the side chains. It does mention that pKa, the values that they list, are for how the side chain would be in a protein, and they're not the pKa's for the free floating amino acids in the cytoplasm. So the aliphatic side chains are ones with the hydrocarbon side chain, and that includes those branched chain amino acids we saw, valine, leucine, isoleucine. Polar side chains, serine, threonine, have the hydroxyl group. Amide side chains, asparagine, glutamine, have the oxygen with the double bond and the nitrogen at the end of the side chain. Sulfur containing, although cysteine and methionine, the sulfur kind of plays different roles. The methionine has a methyl group after the sulfur, and cysteine just has the hydrogen after the sulfur. Aromatic side chains have some kind of benzene ring at somewhere on the side chain. Anion side chains are going to have negative charge and prefix meaning up, so it's up an electron. So those are aspartic acid, glutamic acids. And then your cation, cat meaning down an electron makes it a positive charge. Histidine, which kind of bounces back and forth between neutral and positive. Lysine and arginine, which are pretty much positive at any kind of a normal 7.4 pH cellular environment. This table here shows the pKa of probably all the ones in the list. So you can see which ones are more lower valued pKa, so they're more likely to have a hydrogen stuck to it. Less likely to have a hydrogen stuck to it in the cellular environment. So 7.4 pH of the cell would be more basic compared to the pKa, so there'd be fewer hydrogens around to bond to it, so you'd expect to be missing a hydrogen. And the opposite down here, where there's more hydrogen available at 7.4 pH, so you're more likely to have a hydrogen attached to it. And then in the middle, there's ones that are bouncing back and forth, 50-50 mix of each state. And here's a table where you can sort by the various domains of life. So I'm already sorted by archaea, and you can just pause the video if you want to see, look at the details of this, or go to the Wikipedia page. So there's a slight change in order based on archaea, bacteria, eukaryotes, and then specifically humans. But leucine, serine, kind of at the top, I think, for most all of them, and then tryptophan, methionine, and cysteine at the bottom for the archaea bacteria. And the same kind of abundance is related to which codons code for it. So there's more rare codons can correlate with more rare amino acids. And then there's this plot here, which I talked about before in one of the summaries, I think. So this shows the amino acids kind of on this plot of solubility and size. So solubility is the hydropathy index from this page here, and size is the volume of the molecule. And then the plot shows color coding for the middle nucleobase for the codons. So you can see that for the most part, ignoring the yellow circle, amino acids with similar solubility and size share that middle nucleobase in the genetic code.